So thank you for the introduction, and I'd first like to really thank my colleagues at Recombi who really made this research possible, Peter, Wojciech, Daniel, and Rodrigo, and Pavel. So thank you very much. So as was probably mentioned here, and you are well aware since you're sitting here, recommendations and search share the similar pillars, and those pillars are the embeddings upon which many of your core stack is probably built on. These might include stuff like deep learning recommendation models or vector databases that help you retrieve items that are relevant for your either user's interests or your user's queries. And these embeddings are, well, really useful introduction, might pose severe issues when trying to scale this to very large customer data. And this is because the embedding tables grow along two complementary axes. The first is the cardinality of your entities, be it users or items. And the second is the dimension of the embeddings themselves. If your task grows to situations where you have to deal with, let's say, hundreds of millions or billions of entities, you might find yourself in a situation where even a routine operation like moving to a newer model that likes to produce bigger embeddings is a very costly operation and hurts really your infrastructure budgets, especially infrastructure, because you might notice that locality of data is really important in these systems. And for instance, vector databases that require your that need to be placed in somewhere in your retrieval stack need these embeddings in memory or really close to the system that works with them. And as these systems need to scale horizontally for high availability and so on, these may cause real infrastructure issues for your budgets. So there are many prior works dealing with these issues. So, for instance, low dimensional approximation of really expressive embeddings typically was not really high quality, and you were suffering a lot of quality loss when doing this. But recently, the Matryoshka approach that actually works by like hierarchical retraining of your backbone allows you to compress the embeddings sufficiently, but the training cost might be really expensive for this operation. On the other hand, you can quantize your embeddings to turn them into lower precision storage formats, but these are not hardware agnostic, and it's not easy to move the inference of these structures from one device to another one. And another example is offloading or caching, which while can be made very clever, usually introduces some latency and may, of course, introduce non-trivial system design implications that complicate future work. If you're wondering about the title of our work, it's about presenting a new strategy that can be used instead of any of these, and you might want to try them for your future research. So we introduce CompressSAE, which is a learnable sparse embedding compression method. We, instead of trying to learn low dimensional compression as in standard autoencoders, CompressSAE, based on sparse autoencoders, compresses the dense embeddings into a higher dimensional space, but with few active neurons in each of the embedding dimensions. So this way, the vector is smaller in the memory footprint while preserving the expressiveness of this space, because we actually do not compress the dimensionality in it. So CompressSAE works by, or is formed by an encoder, which is a linear layer with a special activation function that takes only top k most largest entries in this in the activation vector and zeroes out the rest. Then the decoder is formed by a single linear layer without bias, which enables a kernel trick during retrieval. The decoder matrix rows are normalized so that we enforce some regularization in the training loop. The training works by taking a features or embeddings computed and stored in some feature store already available in your system, or by using a pre-trained encoder to generate batches of embeddings. This means it doesn't require new data or raw data during the training, only the embeddings that are compressed representations already, and it requires no encoder retraining, such as Matryoshka-based approaches. The model, while being the model, since it's primarily devised for retrieval tasks, such as the employment of vector databases, needs to reconstruct cosine similarity between the dense embeddings on the input and the reconstructed embeddings on the output. This means the loss function is directly distilling the reconstruction precision from the reconstructed space onto the sparse layer of the embeddings, and the sparse embeddings produced by the encoder are then stored into a vector database that holds sparse embeddings in a compressed sparse format. This network is very fast to train, since it's a very shallow, linear, very small neural network, and it very fastly converges to a high quality approximation of the original input embeddings. The way that we form the network by using a linear bias-free decoder allows us to develop two different ways of retrieval from the sparse database. The first one is a standard dot product based or cosine similarity based retrieval from the sparse vectors, and this is linear in the number of non-zeros in this space, which is smaller than the embedding on the input that we were compressing originally. So it allows us to not only compress the vector database, but also improve the speed of inference. And this is also possible to implement very efficiently using the sparse matrix and vector kernels. Also, the second method uses kernel trick using a special kernel matrix that can basically simulate retrieval in the original space or the reconstructed space by only using the sparse compressed embeddings and the small matrix as a kernel that does a reduced sum for these embeddings. This is more accurate because it's directly tied to the objective, and it's slightly more expensive at k² in terms of the number of active neurons in each embedding. But this might be a very good trade-off in some situation. So in our offline experiments, CompressSAE achieves superior accuracy compression balance compared to Matryoshka-based compression, and it is possible to match performance of even 4 times larger Matryoshka embeddings, especially at really high compression ratios. And final note from the offline experiments is that the reconstructed space retrieval, since it's directly tied to the reconstruction loss objective, is the best overall trade-off in this. And in a production experiment covering roughly 8.5 million users per variant, we tried to compare a 512-dimensional S-BERT baseline with a 700-dimensional nomic model, a 64-dimensional nomic Matryoshka, and an equally large sparse compression of Matryoshka. We observed that both compressed versions beat an 8 times larger S-BERT embeddings in the task, and CompressSAE is capable of sacrificing only roughly 1.5% of the downstream metric compared to the 12 times larger uncompressed baseline from which it was constructed. Finally, we were able to observe that the equally sized CompressSAE model outperforms the Matryoshka by 1.5%, which is statistically significant result. So in conclusion, Sparsity is a promising direction for the embedding-based retrieval, and I really think you should check it out.
So in your approach, is there any way you can control the sparsity when you train the model? I mean, how you control the K?
It's a hyperparameter.
So you just don't have an automatic way to define K for now?
Not yet.